grade, 8.1.1, titled, Is the Graph Linear? So linear actually means, if you remember, linear means kind of straight. It's like a straight line. So we've been dealing with graphs with straight lines, and we're going to be asking that question today, is our graph linear? So here's the intro. It says, have you ever noticed, and this is an important intro. It actually is because it relates to the next problem. Have you ever noticed the sun rises earlier and sets later in the summer than it does in winter? If you live north of the equator, you may have noticed that in December, you often wake up for school while it's still dark, which is what we do. However, if you wake up at the same time of day, in May, the sun is shining, and that's pretty much what's going on right now. The number of hours of sunlight in any one place changes during the year, unless you live directly at the equator. This is because the Earth's tilt changes in comparison to the sun. The number of hours of daylight is approximately equal to the number of hours of darkness at just 2 times of the year, called the fall equinox and the spring equinox. And the spring equinox just happened. Dad, when was the first day of spring? Has it happened yet?
No.
Oh, I thought it happened.
Well, wait a minute.
No, I think it did. I think it was in March.
Yeah, I think it's like, well, we can look it up.
I think it's March something. So that happened back in March. Isn't that when the chime changes? I don't know. No,
Yeah,
it's not. It's not.
Spring forward, fall back.
When did we do that? I don't remember. Oh well.
Look on your phone.
I can't. I'm doing a lesson. The number of hours. Okay. If you compared the average number of hours of daylight, Bailey, to the time of year on a graph, you would be able to see a pattern in how the number of hours of daylight changes. Okay. So today we're going to look at tables, graphs, and situations that change in different ways and build strategies for visualizing different patterns of growth. And Bailey is ready to work on these problems. You ready, Bailey? Okay, here we go. 8-1 is actually a little, I'm just going to say, it starts out nice and then it ends interestingly. Okay, so 8-1, part A. For each of these, A through D, it wants us to look at the situation and then consider how the measurements are related, visualize what it would look like on a graph. So we're going to sketch a graph for each one. Very, very simple sketch. So the part A says, the month of the year compared to the average daily hours of sunlight in the northern hemisphere. So when I was reading that, I figured, okay, well, maybe I'll put month down here and then the hours of daylight right there on the Y. And I'm going to think, well, it just told me in the introduction that I'm going to start in the winter. I think that's what I did, because here's how I started my graph. Say there's 12 hours of sunlight in the winter. So if it goes like that until about spring, and then for spring, the amount of daylight increases till it peaks in summer, because summer, there's the longest day of the year in June. Then once it reaches that, it starts to dwindle down again until it reaches the fall equinox, which then that's supposed to be a straight line. Then it gets to be almost the same daylight darkness hours. So that's what my graph would look like for part A. And that makes sense to me. Hopefully it makes sense to you. Okay. Part B says, the number of months money has been invested compared to the total balance for a bank account that earns simple interest. So I thought this was pretty kind of self-explanatory. So if this was the months again, and the balance is just how much money is in the account at that time. And it's earning interest, which means it's being added. Interest is being added to the balance every month. So that means that my graph is going to go something like this. It's going to go up. I don't know how much interest it's making, but that's it. It could look like that. You could have put it steeper, as long as you're not putting it down like that. Because if you put the line down like that, that means that it's losing money. So if every month we're gaining more interest. So the balance goes up. So that one made pretty good sense to me. So that would be considered linear, especially since it's simple interest, because simple interest is when it goes up by a constant rate. Okay, so then it starts to get interesting here for part C and D. Part C says the cost of an item that has had its price repeatedly increased by 50%. This is interesting. So here's my mistake. I did something weird, and I'm not sure why I did it this way. So I figured, okay, the price starts out here, it stays constant for a little bit, and then it goes up, and then it goes constant for a little bit, and then it goes up. That is incorrect. Because say I have, then I knew that I was wrong because one, I checked the answers, but one, if I made a table with the, I don't know, say it's going up every day. So here's the day and the price. So day one, say the price was $2. Day two, the price would be double this, so that would be $4. Day three, the price would be double 4, which is 8. Day 4, the price would be double 8, which is 16, and one more on day 5, 16 doubled would be 32. So if I graphed that, I'm going to do it really rough. I'm not going to draw dashes. So over 1 up about 2, over 2 up about 4, over 3 up about 8, over 4 up about 16, and then over 5 up about 32. So there's something I'm noticing here which is different from the last graph we did. It is curving up. So this graph would look like a curve, but it wouldn't start on the 0, 0. It wouldn't start at the origin because the price of the toy is not going to be 0. The price of the toy is going to start at, like, I don't know, it could start anything above 0. So that would be our y. So that's what the graph for part C might look like sketched out. We're trying to introduce the idea of a nonlinear graph. So that, I'm just going to leave that up there. And then for part D, this one got a little challenging. But I drew it out, and once I drew out the problem, it started to make a lot more sense. So it says the length of the base of a rectangle that has an area of 24 square centimeters compared to its height. So we're comparing length and height. So I just drew a rectangle. Draw here. I know my area is 24, so I put 24 in the middle. And I know my length and my width. That would be my length and width, the sides. And if I made a table for this, so my L and my width. Actually, did I do L and width? I don't think it matters. It doesn't. Okay, so say my length, I'm thinking to myself, could I ever start at 0? Could this ever be 0? Could this ever be 0? No, it can't, because if you times length times width to get 24, 0 times something is always going to be 0, so you can't start at 0. Anything above 0, you can. So I just did easy numbers. I did 1. If you did 1 times 24, you get 24. If you do 2 times 12, you get 24. 3 times 8, you get 24. 4 times 6, and so on. So I stopped there. So I was like, okay, I'm gonna look at what graph this might look like. So if I did, this is my first x and that's my first y, so I'll go over 1 up 24. Say it's right there. Over 2 up 12, which is about halfway. Over 3 up 8, which is about right there. And then over 4 up 6, which is right there. So this one, instead of curving up, this one's curving down. And it will never touch this axis or this axis because L or W can never be 0. because 0 times anything is always 0, and that cannot be the area. The area has to be 24. So it was a little challenging, but I think we're good. Bringing out a table helps. Bringing out a table helped me fix or figure out those problems. So that was 8-1. 8-2 has an e-tool that you can use, and I think it has a resource page too. Yes, it does. Okay. And once again, the resource page, I know some of you can't print it out, so you can just look at it and then draw the graph, because I think it's just a graph in a table. So it's nice to see the resource page because it gives you a guideline of how to draw the graph. So you're not like, I don't even know how to begin the graph. It'll show you how to do it. Okay. So 8-2 says, now that you've predicted what different graphs will look like, you'll investigate how some of the measures are related. To start, consider this situation. Oscar puts $1,000 of principal in a bank account that earns 2% simple interest each month. So I'm going to start writing this stuff down. $1,000 is the principal, 2% interest. Each month. He wants to track how his money is growing. So principal is kind of a new word. Principal doesn't mean like the principal of a school. It means, in this situation, it means the baseline amount of money that you put into an account. So Oscar put $1,000, so that's called the principal. Oscar's using this formula at the right, and I'll write it in a sec, to calculate how much interest he'll earn on investments that are earning simple interest. So here is the formula for simple interest, and it's I equals P times R times T. And you're going to pretend that there's like an invisible multiplication symbol in between there, but I'm just going to put dots. So it's I PERT. So I stands for interest, and this is all in your book on the right-hand side or underneath, I don't know where it is. So I is the interest, P is the principal, and I would write this down because I'm pretty sure this is on your quiz. R is the rate, and T is the time. So it says he's using that formula, this formula. He knows that simple interest is paid only on the original amount that was deposited, so the principal. For an amount of money that was invested for 2 months, he wrote this equation. And I'm going to write his equation in a different color. He wrote, I'm going to kind of separate that. I equals, and then he wrote 1,000 parentheses 0.02 parentheses 2 equals $40. Okay. Part A, on the resource page or the e-tool, and if you do use the e-tool, I would like you to still write down the table and sketch a graph on your paper. It says on the e-tool or the resource page, complete the table to show the interest he earned after 1, 2, 3, 4, and 5 months. How do you find his new balance each month? So we are going to look at the table now. And I'm going to look at the resource page actually, because the resource page is helpful. And I'm going to write down exactly what's on the resource page. So I'm going to erase this. So the table looks like this. It's a 3-column table. And the first one is month. First column is month. Total interest is the middle column. And the third is bank balance. So that's what's in the bank at that moment after the interest has been added. So for 0 months, there was 0 interest. And this is our starting point. So he has $1,000 in the bank to start. Now it wants us to fill in up until 5. 1, 2, 3, 4, 5. Okay, so what you can do, and I actually made a mistake at first. I wasn't thinking and I wasn't paying attention to detail. And don't make my mistake. I was like, oh, 1,000 times 2% times 2. Okay, so he makes $40 in interest per month. But if you'll notice, that was for 2 months. So that was my mistake. If that had been 1 for 1 month, and you can just do that in your calculator, 1,000 times 0.02 times 1, and 0.02 is just the same as 2%. That's what the 0.02 is coming from. I hope you can see that. It's kind of blurry. So 0.02 is the same as 2%. So 1,000 times 0.02 is actually 20. So he adds $20 each time to the balance. There we go, to the interest. Okay. So after 1 month, total interest is 20, and his new balance is 1,020. The next one's going to be 40 because we're adding 20 every single time. So that's 1,040. 3 is 60, 1,060. 4 is 80, 1,080. 5 is 100, 1,100. So he adds 20 every single time for his interest every month. And that, I think it wants us to sketch the graph. Oh no, it just wanted us to do the table first. So there's the table. Then it wants us to do the graph. So I'm going to erase that. And I'm going to try and make a graph right there. My table's kind of big, but. Okay, so here's the graph. Oh boy, yeah, that's going to be a skinny little graph. That's okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's the month. And this one, it goes by tens. Oof. Oh, it's just doing interest earned. Okay, so if that's just the interest earned, we can go by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, so the month. Let's start with 0 because it starts at 0, 0. There's 0 month, 0 interest. After 1 month, we go up to 20 because we've added $20. For 2, we go up 40 and keep filling it in. Up over 3 up 60, over 4 up 80, and over 5 up 100. And that's our graph, and that's part B. It says, oh, and then we're gonna draw our line, which is not good. It should connect the points. So now it says, what patterns do you notice in the table and the graph? So I said, I noticed that the interest increases by 20 every month. And then in the graph, the interest is the same each month. So a line is formed. I think I'm answering the next question. How can you see each pattern in other representations? So the interest is the same. So the line, the amount of the interest is same. Okay, so we go up, 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 up. If the interest was smaller or larger 1 month, so say the interest was different for like this month to this month, then it wouldn't look like that. It would no longer make a straight line. And in the table, we see it's just a pattern, a repeated addition, 20 plus 20 plus 20 plus 20 plus 20 plus 20. For part D, it says use the patterns you found to predict how long it will take before Oscar has 1,800 in the bank. So for the pattern, so I kind of went kind of a long way around, which I don't know, I guess that's fine. So I want to know which month he would have $1,800. So I know for every 5 months, his interest increases by 100. So if he increased double that, he'd have 10 and he would get 200. And then the next one would be for every 5 again, you'd have 15 and then 300. And then 20 and 400. And I'm going to keep going. And then 25 and 500. 30 and 600. 35 and 700. 40 and 800. So then you'd have $1,800 after 40 months. And you could have done it by tens. Tens might have been easier. So for every 10 months, he doubles his interest. So if you did 10, 200, 20, 400, 40, 800, that would have been quicker. But you could also do it this way. So in 40 months, he will have $1,800 in the bank. Now it says to compare your graph from part B. So from part B of 8-1 to this sketch. So here's the sketch that I did for graph B, which is right there for 8-1, and the graph here, and it looks pretty similar. It says, did you predict the graph would be a straight line? And I put yes. The difference is that 8-1B, I should have put the line here, but it starts on the y-intercept because I believe it was about the 1B was comparing the bank balance. So the bank balance would be on the y. So say it was like $1,000, it would have started over here. So that's my mistake. It should start on the y-axis and then go up. So that's the only difference between this graph and this graph. This graph only does the total interest, it doesn't take account the bank balance in that graph. Okay. On next. Okay. Moving on to 8-3. Oops. I don't want that one. That one. 8-3 says, Anita bought a special baseball card for $8. Later, she decided to sell it, but she wanted to make a profit, so she added 50% to the price that she paid and sold the card to Brandon. When he decided to sell it, he also wanted to make a profit, so he added 50% to the price that he paid for it and sold it to Casey. So Casey increased the price by 50 and sold it to Eli, who increased the price another 50% when he sold it to Fernanda. So another resource page is available, or the eTool. Same idea, we're making a table and a graph of the new price after 5 exchanges. So your table would look like this. This is the number of exchanges, the increase in price, and the new price. And it starts with 0, 0, and this is when the original girl, Anita, bought it, so there was no increase in price, and the price she bought it for was $8. So it wants us to do to 5 exchanges. So 1, 2, 3, 4, 5. So for each time it increases 50%. So each time this is going to increase by 50. Wait a minute. She added 50% to the price she paid. Okay, so she took 50% of this. So 50% of 8, so half of 8 is 4. And then she added that to the new price, which was 12. Okay, so half of 12 is 6. And then add 6 to 12 and you get 18. Half of 18 is 9. 9 plus 18 is 27. Half of 27 is 13.5. 13.5 plus 27 is 40.5. And half of 40.5 is 20.25. and adding that to that gives us $60.75 after the last exchange. So there's our table. And we're going to graph it. So I'm going to put that. Bottom, the x-axis is the number of exchanges. 1, 2, 3, 4, 5. And this is going to be, what did I do it by? I did it by 4s, but I don't think I have enough room. I'm going to do it by 5. No, I can't do it by 5s. I'll do it by 10s. 10, 20, 30, 40, 50, 60. Okay, so let's graph. We're going to do the number of exchanges with the new price. I think that's what they're talking about. Yep, they want the new price. So we're going to graph 0, 8. So 0, 8 is going to be here. 1, 12. Going to be about there. 2, 18 is going to be about there. 3, 27 is going to be about there. 4 and then 40.5 is going to be about there. And then 5, 60.75 is going to be about there. So it's obviously not a straight line this time. So if we were to connect the dots, it's going to go up like that. So there's our graph. It's a curved line. And that was part A. Part B says, what patterns do you notice in the table and the graph? Is the graph a straight line? How can you justify your conclusion based on the table or the graph? So for the graph, they're going up. The new price goes up by a different amount each time. There's no constant rate. So it's not like it's 8 plus 4 plus 4 plus 4. It goes 8 plus 4, then plus 6, then plus 9, then plus 13.5. So that's the difference in the table. And the graph is obviously different. It's curved. It's not a straight line this time. Part C says, how does the graph you made in this problem compare to your sketch from part C of problem 8-1? So part C of 8-1 was very similar. It kind of looked like the same thing. It was like a curve up. Did you predict the graph would curve? Well, we predicted this graph would, but I wasn't so sure about that one if it would curve, but it obviously does. So part D says, how much did Fernanda pay for the baseball card? So Fernanda paid 60.75. No, Fernanda was 4, right? Who was Fernanda? She was, so I went from Anita to Brandon, that's 1. Then to Casey 2. Casey to Eli's 3, and 4 to Fernanda. Oh, so Fernanda was exchange 4. So she paid $40.50 for the baseball card. And that's part B. And the last problem is 8-4. And we're talking about the curving of the graph again. Oops. And it says, in problems 8-2 and 8-3, one graph made a straight line while the other curved. Part A, how is the situation that created a straight line changing? How is it growing? So it was growing in 8-2. It was growing $20 per month, right? Yeah. Per month. The interest was growing $20 a month. Part B, so it says growth that creates a straight line shows constant change, and it's called a linear growth. So this was a linear growth. and I'll put a straight line. What made the graph in problem 8-3 curve? How did the growth show in the table and in the graph? So the graph, I put in 8-3, the graph curved because, and you might know this already, the rate was not constant. It went up differently each time, and we saw that in the last graph. So it was not a constant rate, it was inconsistent. That means the graph curved up. Shouldn't have put that one there. There we go. All right, and that, I believe, is the end of 8.1.1. And thanks for watching. See you later.